Good morning. I'm Dr. Sandrine Bernardini. I'm a French associate professor. I'm in the French chapter board of IEEE Sensor Council, and today I will present you our work on barium titanate sensitive film for carbon dioxide detection. This work has been done at Aix-Marseille University, which is an university located in the south of France, in Marseille. It's a huge university with more than 80,000 of students. We are involved in CIVIS European project with 8 universities for researchers and students. I'm working at the Institute of Materials Microelectronic Nanoscience of Provence, IM2NP, in Marseille. And this lab is more than 300 scientists working from the fundamental physics to applications. The lab is divided in 5 departments and 19 teams, and I'm working in GTech department in the microsensors and instrumentation group. Today I will present you our motivations, the methyl oxide sensors and the materials we have chosen. I will move on our structural and electrical characterizations, and I will conclude and give you a perspective. So why we have chosen carbon dioxide gas? Because it's a toxic gas, it's odorless, colorless, and we have all around us an average concentration around 400 ppm, and it's a gas with high thermal stability. Is the cause of the global warming and greenhouse effects, and the outdoor air monitoring is a major social issue because it affects our health. We can have some headaches or the risk of death after prolonged exposure to carbon dioxide. There are also commercial instruments. Most of the technologies are based on infrared detection. It's high performances and high selectivity to carbon dioxide. However, the cost is still high, and we can't miniaturize this infrared detector, and they have a high power consumption. And because we are working in my group for several years now in methyl oxide gas sensors, we have decided to check if we can detect the carbon dioxide with this kind of sensors, which are low cost process. We can miniaturize them, we have a low electrical consumption, and we can obtain a high sensitivity. The sensing materials is the following. Operating principle, we have a substrate and methyl electrodes on the top of the substrates in contact with the sensitive layer. So we can detect if we have the change of charge. We're going to have a target gas around this sensitive layer, and if you bring enough energy, you can have activate the oxidoreduction reactions between the gas molecules and the sensitive layer. So you have charge transfer and you have variation of the conductivity in the sensitive layer. So if you look here, the variation of the resistance versus time, if you have an N-type semiconductor like tin oxide and you bring an oxidizing gases at the surface of this semiconductor, you're going to have an increase of the resistance, and when you switch off the gas, you expect to have this decrease of the resistance coming back to the baseline. In my groups, we are working on different methyl oxide materials like tin oxide, tungsten oxide, zinc oxide, copper oxide, and barium titanate. So why we have chosen barium titanate? If we look at the literature, you can see that different works have been done with these materials, but sometimes with high temperature, operating temperature, or with capacitive methods, and with high concentration of carbon dioxide. In our case, we're going to try it around 280 degrees. with resistive method and with 400 ppm. The first step of this study was to fabricate solution with barium titanate with this material alone. So we bought nano powders from Sigma Aldrich. We mixed it with the ethanol and glycerol, and we drop it on a transducer. You have here the picture of our transducer with the platinum interdigitated electrodes. We adjust the viscosity of our mixture, and we anneal it during 3 minutes at 450 degrees, and then we measure the thickness of the thin film obtained at the end, and it was a thick layer around 15 micrometer. After that, we make an XRD diffractogram, and we obtain different peaks. So we have a crystalline thick film. And if we compare with the literature and reference value of these peaks, we can see that we have a tetragonal phase for this barium titanate thick film. Here I present you our experimental setup. We have an automated bench with a generation system, 3 channels, 3 gases, carbon dioxide, carbon monoxide, and nitrogen dioxide, and we can have different dilution with a dry air gas vector. We have a climatic chamber where we can control our environment, the temperature and the relative humidity. And we have a test chamber with multi-channel acquisition system, and we have a PXI and a LabVIEW program to control it. And here this is the picture of the generation of humidity. If you look the resistance response we obtain for 400 ppm of carbon dioxide, here we have an increase of the resistance when we put the gas on, and when we switch off, we return to the baseline. So we don't poisoning our surface. And also we can say that, like in the literature, we have an oxidizing gas and an N-type semiconductor. This work has been done at 280 degrees and 50% of humidity, which is the value used for the manufacturer in industry when they make the tests. If we want to optimize our parameters, we can see here on this graph that the sensor response increase when you increase the temperature is a linear increase. However, we can't go above 280 degrees because we have a risk of burning electric wires inside our chamber. So we decided to stay at this value to make our measurements. And for the sensing mechanism, we can see here the equations that where we can find that we need water, we need humidity to have the carbonation of the carbon dioxide. Here, this is a response versus the concentration of carbon dioxide. We have an increase of the response when we increase the concentration. And here it was for an exposure time of 5 minutes. We study also the repeatability of the sensor for 1,500 ppm of carbon dioxide. And we have here a good sensitive response with a good repeatability with a coefficient here equal to 1.24%. If we study the response versus different relative humidity, here you can see that the highest response is obtained for the lowest humidity. Here you have also zoom on this part. 400 ppm of carbon dioxide, and the higher response is for 20% of relative humidity. So in conclusion, we have shown you that it's possible to detect carbon dioxide at 280 degrees with the barium titanate solution, thin deposition to obtain a thin film. We obtain a tetragonal structure for a thick film. We have an increase of the response with increasing our concentration and a good repeatability of the response of this sensor. In the future, we would like to use different deposition method with the solution to enhance the aging of the sensor, and we would like also to add some materials on the top of this barium titanate film. To finish, I would like to thank all the people I work with, my PhD students, Fabien Le Pennec, my master student, El Halabi Amine, and my colleagues, Dr. Perrin-Pellegrino Carine, for her experience in XRD measurements, and Professor Aguir Khalifa and Professor Bendahan Marc for the fruitful discussions. And finally, I would like to thank you for your kind attentions, and thank you very much. If you have some questions, I can answer to them. So please don't hesitate, and thank you for your kind attention. Goodbye.